Dear students, so let us today we study on X-ray diffraction and determination of crystal structure restricted to cubic system. Before to start with this, let us we know the two important terms in this. One is known as isomorphism and another one is polymorphism. Iso means generally the term same or similar. The crystalline substances which have similar chemical composition are found to possess the same crystal shape. Example, sodium phosphate, formula Na3PO4, and sodium arsenate, Na3ASO4. These two substances have similar chemical composition and they are found to possess the same crystal shape. These two are the examples of isomorphous compounds, and the phenomenon is known as isomorphism. There are certain substances which exist in more than one crystalline form, which are formed under different conditions of temperature and pressure. This phenomenon is known as polymorphism. I repeat, there are certain substances which exist in more than one crystalline form, which are formed under different conditions of temperature and pressure. This phenomenon is known as polymorphism. For example, if I take the carbon exists in two crystalline forms called the graphite and diamond. Similarly, calcium carbonate exists in two crystalline forms called calcite form and aragonite form. So these are the examples of polymorphism. Suppose if the polymorphism is exhibited by the elements, it is called allotropy. The word allotropy is for the elements in general, which is having the same meaning of polymorphism. Whereas in case of chemical compounds, if they have the crystalline structure, then the word polymorphism is generally used. That's why below I have given an example. Graphite and diamond are the examples of allotropy as well as polymorphism. Rhombic sulfur and monoclinic sulfur are the examples of allotropy or polymorphism, but calcium carbonate, which exists as calcite and aragonite, is an example of polymorphism only, but it is not allotropy. So this is the meaning of the isomorphism and polymorphism. Coming to the X-ray diffraction and determination of crystal structures. In 1912, a German physicist, Max von Laue, suggested that a crystal could serve as a three-dimensional diffraction grating provided the wavelength of incident radiations and the distances between consecutive atomic layers in the crystal were of the same order of magnitude. X-ray with a wavelength approximately 0.1 nanometer or 1 angstrom fulfill this condition. Making use of this, the structure of the crystal can be determined. William H. Bragg and his son William L. Bragg developed a simple equation for the study of crystal structure. According to them, a crystal could be employed not only as a transmission grating but also as a reflection grating. When X-rays are incident on a crystal face, these penetrate into the crystal and strike the atoms in successive planes. From each of these planes, the X-rays are reflected like the reflection of a beam of light from a bundle of glass plates of equal thickness. Based on this model, they derived a simple relation between the wavelength of the incident X-ray and the angle of incidence, that is theta, and the distance between the two successive atomic planes, that is the d. So they derived the equation known as n lambda is equal to 2d sine theta, where n is an integer known as the 1, 2, 3. It's called the first order reflection, second order reflection, and so on. This equation is called the Bragg's equation or the Bragg's law. Now let us study how this derivation of the Bragg's equation can be done. Go through the diagram very carefully. You have a plane 1 and you have a plane 2. So in this, a beam AB strikes on a plane 1 and the another wave it strikes, that is DE, it strikes on the plane 2. And accordingly further they undergo reflection. AB it reflects into BC and DE it reflects into EF. So go through this diagram carefully. I am going to explain this diagram. Consider the two waves 1 and 2 incident on planes 1 and 2 respectively at an angle theta. The initial part of the two waves AB and DG are in phase. The wave 2 reflected from plane 2 travels a greater distance than wave 1 reflected from plane 1. So that excess deflection is this. So it travels from GE to this. So this is the extra distance, whereas the plane 1 it comes and it reflects here, but in case of the plane 2 it travels from here and goes to here. This is the extra distance that it travels. This is what it says. Now, drawing BG perpendicular to DE. See the diagram. Drawing BG perpendicular to DE. It can be seen that the path difference delta of the two waves is GE plus EH. GE plus EH is the pathway. Next, the part of the reflected wave BC and HF must also be in plane. So below I have given a diagram. So the part of the reflected wave BC and HF must also be in phase so that the two waves reinforce each other. This is possible when the path difference delta is either a one whole wavelength or any integral multiple of it. that is n lambda. Therefore, from this we can say n lambda is equal to GE plus EH. So the n lambda which I have shown is nothing but here GE plus EH. This is the extra, the distance what it travels, the wave, when it attacks to the second plane. From the figure, angle GBE is equal to angle ABD, that is equal to theta. So this is nothing but 90 minus angle DBG. Similarly, angle HBE is equal to angle CBF. This is also equal to theta. Since the two right-angled triangles BGE and BHE are congruent, therefore GE is equal to EH. Next, we can write it the same thing as GE upon BE. GE upon BE is equal to GE upon, what is BE? BE is nothing but it is the distance between the two planes. That distance between the two planes is given as D. So therefore we can write GE upon D. This is equal to sine theta. Therefore GE is equal to D into sine theta. Now, what is GE? We can also write that multiply the above equation by 2. That is 2GE is equal to 2D sine theta. Just I have multiplied both LHS and RHS by 2. Since we know 2GE is nothing but it is the path difference. So therefore we can write 2GE is nothing but it is a GE plus EH. So the GE plus EH is nothing but it is the n lambda, as I have given in the point number 5. So instead of 2GE, I can write n lambda. Therefore, we get n lambda is equal to 2D sine theta. This is nothing but the Bragg's equation. So n is equal to 1 indicates the order of reflection is first order. N is equal to 2 indicates the order of reflection is second order, and so on. A very simple derivation. Students, you must know how to derive this equation. This will be generally asked in the examination. So here I have given a very clear-cut indication of this. So that is in this case the angle, the additional path length traveled by the wave striking lower surface is 2d sine theta. So this is what we are measuring here. This is the part. Okay. So this is the Bragg's equation. This is the plane 1. This is plane 2. This is the incident angle of plane 1, incident ray of plane 2. This is the extra distance what it travels. This is nothing but n lambda. That n lambda is nothing but 2d sine theta. The same thing is also given in another way in this diagram. Now, after knowing the derivation of the Bragg's equation, now let us take another using this X-ray diffraction studies, how to determine the crystal structures. So let us restrict our study to the simple cubic structure, body-centered cubic structure, and face-centered cubic structure for this. Now, using X-ray diffraction method, there are 3 ways of finding the crystal structure, and those 3 ways are the first one is the law method, another is rotating crystal method, and third one is X-ray diffraction powder method. So here below about the law method and rotating crystal method and powder diffraction, what are the similarities and the differences are given. So the law method includes the orientation, single crystal, polychromatic beam, and it contains the fixed angle. In case of rotating crystal method, the lattice constant single crystal should be used. Monochromatic beam of X-rays are used. We get variable angles. And in case of the powder metallurgy, you have lattice parameters are used. It contains polycrystalline. The powder contains large number of crystals. And we are using monochromatic beam of X-ray. And here also we have variable angles. Now coming to the determination of crystal structure by loss method. The loss method is mainly used to determine the orientation of large single crystals. X-ray or white radiation is reflected from or transmitted through a fixed crystal. The diffracted beams from arrays of spots lie on curves on the film. A crystal is mounted in the path of the X-ray beam. Each atom in the path scatters or deflects some of the X-rays from their original path. The X-rays are then made to leave an impression on photographic film placed at some distance from the crystal, and the film is then developed. Due to diffraction, it shows a pattern which is uniquely characterized of the crystal investigated. It is just like a fingerprint of the every person we have. It is a fingerprint of every crystal. It is having a unique structure. Based on that fingerprint or unique crystal structure, we can find out this crystal is having this structure. The big spot in the center of the pattern corresponds to the unscattered beam. The other spots represents the scattering part of the original beam through various characteristic angles. The pattern so obtained depends on the symmetry of the crystal. From this pattern, crystal structure could be obtained. Yes, here I have shown. So the law, a great scientist, so he got the Nobel Prize in 1914, and here he used this X-ray and he passed the X-rays through a crystal, and that crystal gives a spot. This spot is a characteristic feature of the crystal. So based on this spot, we can find out what would be the geometry of that crystal. Here also I have shown the same thing. This is the X-ray generator. So it produces, these X-rays are passed through a crystal, and the crystal develops a particular shape. Here also you have the crystal is developing a particular shape. So based on the shape of this, we determine what would be the structure of that crystal. This is given by the law called the loss method. So here it shows the crystal is taken here, and this crystal, when X-rays are passed, it develops a elliptical shape, and the arrangement of atoms, based on this arrangement of atoms, so we can find out the geometry of that crystal. There it says, in the transmission law method, the film is placed behind the crystal to record beams which are transmitted through the crystal. In the transmission law method, the film is placed behind the crystal to record beams which are transmitted through the crystal. One side of the cone of law reflection is defined by the transmitted beam. The film intersects the cone with the diffraction spots generally lying on an ellipse way. The same thing here I have explained about this method. Coming to the second method, that is determination of crystal structure by Bragg's rotating crystal method. Here the table is rotated and the particular angle where the X-ray scatters or it deflects, that angle is measured. The apparatus used in this determination of crystal structure by rotating crystal method is shown in the figure. So the figure is, this is the figure. So here the X-rays are passed and this is the crystal is there, and that crystal, it gives a deflection, and that deflection is at 2 theta, and this angle is theta, and that is detected in the detector. Similarly, this diagram, and this diagram, all the three diagrams are the same. So this is the, what you can say, the apparatus is used in this method. The X-rays generated in the tube is made monochromatic by passing through a filter and then through the slits to get sharp and narrow beams. The X-ray beam of known wavelength is allowed to strike the crystal mounted on the turntable, which rotates with uniform angular rate. The rotation causes sets of planes coming successively into their reflecting positions. The intensities of the reflected rays are measured on a recording device. Generally, it is an ionization chamber, and glancing angle theta for each intense reflection is recorded. For a given angle of incidence, the angle of reflection is 2 theta. For given angle of incidence theta, the angle of reflection is 2 theta. For a particular phase, there will be a set of theta values which satisfies Bragg's equation and for which intensities will be maximum. This corresponds to different values of n, since intensities decreases as n increases. Knowing n, lambda and theta, we can calculate the distance between the two successive planes, that is d, of the crystals, which gives the crystal structure. Here I have given for simple cubic structure, the planes passing through the atoms are D100 is A, D110, this is on x-axis, D110 is A upon root 2 and D111 is A upon root 3. So these are known as the Miller indices and the values are given. How you get these values, so that you are going to learn in higher standards, where A is the distance between the two planes. For simple cubic structure, so it is the values are 1 is to 0.707 is to 0.577. This is very important and students must Remember this. For any crystal having cubic structure, there the Miller indices for the three axes D100 is to D110 is to D111. So the values are 1 is to 0.707 is to 0.577. This is theoretically calculated. For face-centered cubic structure, these values are 1 is to 0.707 is to 1.154. For body-centered cubic structure, so these values are 1 is to 1.414 is to 1.577. These values, as I have said, you are going to learn in higher studies how you get A upon 2, A upon root 2. So, you have to remember for simple cubic, the ratio, for body-centered cubic, the ratio, and the face-centered cubic ratio. And through the experiment, we calculate the angle. Based on the angle, so we calculate the distance. In order to find out the type of the cubic lattice in the given crystal, the angle at which the first, second and third order reflections that takes place from different planes are studied. The values of D100, D110 and D111 are calculated using Bragg's equation. That is, D is equal to n lambda divided by 2 sine theta, where n is the order of reflection. The ratio D100 is to D110 is to D111 is calculated through the experiment and compared these values with the theoretical values as given above for different types of lattices. So, based on this, so comparing this, we come to know what would be the crystal structure for that particular crystal. So, this is what the rotating crystal method, the apparatus that is used. So, this is, as I have explained about the rotating crystal method, how it is calculated. So, this is also about in the rotating crystal method, a single crystal is mounted with an axis normal to A. Monochromatic X-ray beam, a cylindrical film is placed around it and the crystal is rotated about the chosen axis. As the crystal rotates, sets of lattice planes will at some point make the correct Bragg angle for the monochromatic incident beam, and at that point a diffracted beam will be formed. Now coming to the third one, the determination of crystal structure by powder diffraction method. Here also in all the second and the third case, we calculate the angle. In the first case, we have a particular, what you can say, the shape we get. This method is used when a single undistorted crystal of a solid is not available. So, all the solids will not crystallize properly. Some of the solids we get in the form of a powder. In such cases, this method is used. In this method, the powdered crystalline substance is taken in a capillary tube and placed inside a camera containing film strip. The sample is rotated with the help of a small motor. X-rays pass through the gap between the ends of the film strip. The powder containing some of the small crystals will reflect X-rays from each lattice plane simultaneously. The reflected X-rays will make an angle 2 theta with the original direction. Lines of constant theta are obtained on the film. From the design of the camera, theta can be calculated for different crystal planes, which is further compared with the standard theoretical values. Based on this, the type of the crystal lattice is predicted. So the last point, we calculate the theta, and remaining procedure is same as I have explained in rotating crystal method. So this is what the meaning. Here this is a camera strip. So the X-ray is passed here. This is the sample is taken here in the form of a powder and the placed, and it is allowed to rotate. So this is here we get the plans how the strips. The same thing is also given in these two examples. So based upon these patterns we get, and comparing this with the theoretical values, we come to know what would be the structure of that crystal. The same thing, the powder method is given here. Now let us explain this taking some examples. Number one, the first order, it's a problem. The first order reflections from 100, 110 and 111 planes of a given cubic crystals were found to occur at angles 5.9 degree, 8.4 degree and 5.2 degree respectively. Now here the theta values are given. Determine the type of a cubic lattice to which the crystal belongs. It says for first order reflection, therefore n is equal to 1. And we know that here you have to find out the distance. D is equal to n lambda upon 2 sine theta. So here n is 1, therefore we get lambda upon 2 sine theta. So what is the theta value for 100 plane? It is 5.9 degree. So lambda upon 2 sine 5.9 degree gives the sine 5.9 degree is the value 0.103. So lambda upon this gives 4.854 into lambda. So for D110, so sine angle is 8.4 degree. Substitute that value, you get 3.425 lambda. For D111 plane, we get 5.319 lambda. In all the cases, the lambda is a constant. It is taken out. The ratios D100 is to D110 is to D111 planes. The D values are 4.845 is to 3.425 is to 5.319. Here the first value is the A. So you divide that value to all the numbers. So 4.845 divided by 4.845 gives the value 1. Similarly, 3.425 divided by 4.845 gives the value 0.706. And finally, 5.319 divided by 4.845 gives 1.096. You see this ratio. This ratio is very close to that of phase-centered cubic lattice given by the theoretical way. Hence, the given crystal has phase-centered cubic structure. This is how the problem is to be solved. Let us take another example similar to this. The first order reflection from 100, 110 and 111 planes of a given cubic crystals were found to occur at angles 5.9 degree, 8.4 degree and 10.5 degree respectively. Determine the type of cubic lattice to which a crystal belongs. Here once again n is equal to 1. Calculate D100 and we get 4.845. For D110 we get similarly 3.425 and D111. So the value you get 2.747 lambda. Now the D100 is to D101 is to D111. The values you write and you divide that value by 4.845. Why we divide the value by 8.455? Because that is a value of A. So we get the ratios 1 is to 0.707 is to 0.567, which is very close to the simple cubic structure. So this ratio is very close to that of simple cubic lattice. Hence the given crystal has a simple cubic structure. This is how the crystal structures are determined. Coming to the third example, here sometimes they ask the distance between the two planes. That's all. The second order reflection of X-rays from 100 plane of sodium chloride occurs at 29.3 degree. If the wavelength used is 1.54 angstrom, calculate the distance between the two successive 100 planes in sodium chloride. Here the problem which are the given, the second order reflection, that means n is equal to 2 and the lambda is given 1.54 angstrom and theta is given 29.3 degree. So we know n lambda is equal to 2d sin theta. So we want to calculate d. So d is equal to n lambda upon 2 sin theta. So that's equal to n is 2 and lambda is 1.54 divided by 2 into sine 29.3. So this, if you simplify, we get 3.149 angstrom. So this is the distance between the two successive planes in sodium chloride crystal. Students, go through these aspects and try to learn about these things.